Okay, so last time we talked about work and power. Now this time we're going to talk about mechanical energy, WorkEnergy Theorem, and conservation of energy. All right, so starting with mechanical energy, it's going to be the idea that we're looking at just energy right now that's due to position change or motion, or it could be both. There are other types of energy that we could be looking at, thermal energy, heat, chemical energy, nuclear energy, electrical energy. Some of these we'll talk about later this year, but right now we're just looking about mechanical things. So the idea of an object, moving from one point to another. Springs are able to be wound up or stretched and store energy. You can lift a weight or lift a book or lift a ball to some height and store potential energy in it. And that's what we're looking at with mechanical energy. Okay? So potential energy is that stored energy. It means it has the potential for doing work or causing motion. Whereas kinetic energy is the energy the object has when it is in motion. So this gets us the idea of work-energy theorem. So we've already talked about the fact that work changes energy. But as a theorem, what it states is that a gain or loss of energy is the result of work being done on an object. Right? So simply put, work will change the energy. The work could change the kinetic energy, so delta Ke means change in kinetic energy. The work could change the potential energy, delta Pe, or the work could change both, delta Pe plus delta Ke. All right? So to increase speed, a change in Ke that's positive, work must be done on the object. To decrease speed, again, change the kinetic energy. We want to reduce the kinetic energy. Work must be done on the object. To lift something up, we want to change the potential energy due to gravity. Work must be done. To stretch or compress a spring, PES, work must be done. Okay? So the work that is done to bring a moving car to stop is the force of friction times the stopping distance. If the initial speed of the car was doubled, the stopping distance is actually less, about the same, twice, or none of the above. So it ends up being none of the above. Now, instinctively, most of you probably figured, well, if the velocity or the speed went up by a factor of 2, well, shouldn't that mean that the work went up by a factor of 2? But that's not the case. And we're going to find out because of how we actually define kinetic energy. It actually ends up becoming a factor of 4 that it increases by. It quadruples. So when you're speeding down the highway, the difference between going 30 miles per hour versus 60 miles per hour, there's 4 times as much energy in that car going 60 as there is in that car going 30. So kinetic energy, again, is the energy of an object in motion. So the kinetic energy is going to depend on the mass of an object and the square of its velocity. So this is where that quadruple factor comes in. So if I double my velocity, it's that doubled squared. So 2 squared is 4. Right? Whereas if I had tripled my velocity, 3 squared would have been 9. So kinetic energy is 1/2 mv squared. All right? So must a car with momentum have kinetic energy? Yes, due to the motion alone. Yes, when the motion is non-accelerated. Yes, because speed is scalar and velocity is a vector quantity, or no. And the correct answer is yes, just in motion alone. So when a car has kinetic energy, it has to also have momentum. That's just due to the fact that it has motion alone. We also have potential energy. Gravitational potential energy is the type of potential energy due to gravity. So if I lift something up above the earth or above, we consider ground level, we have potential energy due to gravity, elevated position. So examples of this are water that's dammed up in a reservoir, lifting a weight in a grandfather clock. And in this case, the work here has to be equal to that force of gravity times that vertical distance we've lifted it. So the vertical heights or vertical distances we should consider y. We're lifting that mass against gravity, g, so our potential energy due to gravity is mgy. So, does a car hoisted for repairs in a service station have increased potential energy relative to the floor? Yes, no, sometimes, or we don't have enough information. Well, the answer is yes, because from here to here, this was 0, this is some height y, the car has some mass, and gravity's pulling on it. So whatever height I've lifted it, I've given it some y, so I'd have a PE grav of mgy when it's lifted off the floor. Now, what would actually do that work? Well, the air compressor pushing on the hydraulic fluid. That's what would push the piston up. So, some other examples of potential energy would be if I have a 10 Newton ball and I want to lift it 3 meters. Okay? I could just lift it straight up 3 meters. I could push it up a ramp where the height at the top of the ramp is a vertical displacement of 3 meters, even though the length of the ramp is 5 meters long. Or I could lift it upstairs one at a time, bloop, bloop, bloop. As long as at the top they all have the same vertical change in height, 3 meters, I'd have the same change in potential energy. So in this case, if I went through and did this, PE grav would be 10 newtons, that's my mg, times 3 meters, or 30 joules for all 3 cases. So now spring potential energy, PES, is a little bit different. So this is the potential energy due to stretching or compressing a spring. And we have to remember Hooke's law to understand this. So Hooke's law told us that the force of a spring was equal to negative kx. So that means the work I have to do to stretch or compress a spring is positive kx, because I'm the one that's putting the energy into that spring. I'm the one doing the work on that spring. Okay. Now, if a spring starts at 0, displacement means it starts with 0 force and goes to kx, that average force between 0 and kx is half of kx. So if I plug in the force as half of kx for a distance of x, my work comes out to be 1/2 kx squared. So that's the work I did to change the energy of that spring. So that means the stored potential energy in that spring, sometimes called the elastic potential energy, is 1/2 kx squared. So, conservation of energy. So the law of conservation of energy basically states that if we're not doing work on the system, so we're not taking any energy away from the system, we're not adding energy back to the system, that the energy can only transform from one form to another. So if I lift a weight up to a height, or like the barrel of bricks in the barrel of bricks video, up to a height, it has PE, okay, PE from gravity. If all of a sudden something makes that rope let go and that now can fall, that PE grav can only change into another form of energy, in this case, kinetic energy. Okay? So it's the idea that the initial energy of a system equals the final energy of a system, if we're taking into account all forms of energy. So for our case here, though, we're only looking at the mechanical right now. So our idea of E is just kinetic and potential. So KE initial plus PE initial has to equal KE final plus PE final. So we're assuming there's no losses due to heat or friction and no gains due to some external forces. So no motors, no explosions, no other external work being done to the system.